Okay, so to start off class today, I'm going to ask you to draw a quick sketch of an action potential. So a quick sketch of what we were doing on Monday. So what you want to draw is make sure that you have down our phases. So you want to have down the depolarization, the repolarization, and then the hyperpolarization or the after hyperpolarization. So just a reminder for these axes as I start to draw with you. When we're talking about an action potential, we're talking about a wave of charges running down the neuron. And when we're drawing out a graph of the action potential, we're talking about what's happening over time on a single patch on our neuronal membrane. So our x-axis is time. Our y-axis is that charge, so in millivolts, our membrane potential. Membrane potential. So we have a couple key numbers that we're paying attention to. So at rest, our resting membrane potential, where we start, are at -70. Then we have a threshold that we're trying to hit of -55. And our action potential is going to spike all the way up to +30. So see, these are our sort of key waypoints that we're going to pass as we think about the phases of the action potential. So when we would begin, we're going to start out at our resting membrane potential of -70. We're going to say that we depolarize to -55, which is when we know that we're going to kick off the action potential. Okay. So depolarization continues. We see a spike up to +30. So this phase would be the depolarization, right? So this going up is the depolarization. There we have our depolarization. So repolarizing the cell, we go back down. So repolarizing, going back to where we were. So for repolarization, we're going back down. Take us down to here. That's our repolarization. And then we actually overshoot a little bit. So our hyperpolarization or our after hyperpolarization. So we continue below -70 until eventually we restabilize at that resting membrane potential. So this curve is what we're going to see every single time we see an action potential. Those are our phases. And we spoke last time, this is really due to changes in the permeability of the membrane to our ions. So we know that as we're thinking about this first phase, the depolarization, right? We have sodium ions coming in. So we have increasing permeability to sodium ions, right? Then those sodium ions, their channels, their voltage gated channels swing closed. So they're swinging closed here at the peak. Then we end up with a lot of potassium rushing out, which is why we're going down, repolarizing, and then hyperpolarizing. If we wanted, we could additionally draw on our permeability curves here, but I'm not going to do that for right now. So we're going to keep talking about our action potentials. So that is the shape of our action potential. This is how we send a signal down a neuron. And what we want to know about this additionally is that when we talked about our graded potential, so when we talked about adding up to get to threshold, we were summing graded potentials either spatially, so two signals coming in from two different places, or temporally, two signals coming into the same spot in time, but like kind of overlapping their effects. When we have an action potential, that's not how it works. An action potential, we say, goes by the all or none principle, which is just there is an action potential or there isn't an action potential. There's not a bigger one or a smaller one. It's just a switch that's on or off. That's it. So that's why I could draw those numbers on without knowing anything else about our action potential. As we were warming up, we're always interested in those same charges, that -70, -55, +30. And so they're always going to be the same. So the threshold is that minimum depolarization to induce the regenerative mechanism for opening of sodium channels, aka we have to reach threshold to kick off the action potential. But once we do, that action potential is always the same. It's always the same height of the peak. We can describe how much the initial depolarization changed the membrane. So we could talk about like how big were those graded potentials that got us to threshold. And if we did that, we might use these terms up here. So a sub-threshold depolarization, sub below threshold, that's telling us that when we add up the graded potential, we're not getting to threshold, we're not getting to -55, so no action potential happens. Supra meaning above here, so the supra-threshold depolarization, supra-threshold gets us to above that threshold of -55, so that is when we do kick off our action potential. Okay. So if we had just a threshold depolarization, we got us to exactly -55, we'd still kick off an action potential, but it would be the exact same magnitude, so the exact same height, that exact same spike, as one that got us all the way to -40 with our graded potentials. So that action potential that we kick off, whether we just get to -55 or whether we get above it, is still going to look the same every time. So when we talk about signals from neurons being stronger or weaker, we're never going to be talking about the height of the action potential. We're never going to be talking about how big that amplitude is, how big that magnitude in charge is. The way we're going to send a stronger signal to our next cell, we're actually going to increase the frequency of action potential. And we'll talk about that in a bit. So action potentials can sometimes get closer together, but they're never going to get taller. So when we reach that threshold, an action potential happens. The size of the stimulus, so the size of that graded potential that we're causing as something is signaling our neuron, not going to affect the size of the action potential. We're always just going to positive 30. So we've seen this image before when we were thinking about graded potentials. Right, so here we saw a little bit of a graded potential, didn't get us to threshold, so we have no action potential. So we could call that a sub-threshold stimulus. These two things go together. Okay. Same thing for the second one. This is still below the threshold, so this is still a sub-threshold stimulus. This one was a threshold stimulus, so it got us just to our positive 55. That's what we know this because it tells us that it's a threshold stimulus. Our suprathreshold stimulus, the only way that we know that it's suprathreshold is because we've been told it's a suprathreshold stimulus. The reason that we can only tell that by being told is because the action potential is exactly the same, right? So this action potential from our threshold stimulus and this action potential from our suprathreshold stimulus look exactly the same. They're going exactly between these same different waypoints, these same different levels of charge. Okay. Take a quick look at some of this stuff in 3D. Okay. Right, let's get that as soon as we can. We can also go through this in flowchart form. All of this is all just talking about the same action potential that we've been talking about. Just trying to get it to you in different ways, hoping one of these clicks, right? So what we're starting out with, the top, our initial stimulus for the action potential is going to be reaching threshold, so a threshold stimulus. So we added upgraded potentials. We got to at least -55. This depolarized the membrane to threshold. Okay? So depolarized to -55. Once we are at -55, this triggers our voltage-gated sodium channels because they are responsive to that charge. And their response to depolarization to threshold is to open more voltage-gated sodium channels. So our sodium channels open. Sodium has a strong electrochemical driving force to move into the cell as soon as we open sodium channels. It always wanted to get in, now it can because we have open channels. So we would say that we have increased the permeability to sodium, and therefore sodium is now able to follow that driving force and it flows into the cell. The effect on the cell overall now, or on this patch of membrane, is that we are increasing the membrane potential because we're moving positive charges in. So this is that depolarization phase. We have a net positive charge. So that's our first piece that is happening. And this is a positive feedback loop because as we depolarize more and more voltage-gated sodium channels are turning on and sensing this change. So this over here is a positive feedback loop, opening more and more and more and more sodium channels. Okay. This does have to turn off eventually. So there is a delayed effect on our inactivation gate. So to open these sodium channels, we opened our activation gate, right? Meaning that both of our doors essentially on our sodium channel were open. After about a millisecond, the inactivation gate swings closed, closing the sodium channels because now we don't have a way through anymore. So this delayed effect of hitting that depolarization is that our sodium channel inactivation gate closes, which means that our sodium permeability is dropping. So we are stopping sodium, right? So this is a down arrow, stopping sodium from flowing into the cell. At the same time, we have something happening with our potassium. So in response to this depolarization of the membrane, we also had voltage-gated potassium channels. They don't open for a while, right? So the sodium channels start out doing their thing, this depolarization phase, but there's this delayed effect. And at about the time that we're getting to +30 with that peak of the action potential, our potassium channels are opening. We have this delayed effect opening potassium channels. And the force on potassium is in the opposite direction from sodium, right? So potassium wants to leave the cell. That's the direction for its electrochemical driving force. So when we open these potassium channels, when we increase the permeability of the membrane to the potassium flows out of the cell. So potassium wanted to get out of the cell, now it can flow out of the cell more. Okay, so flowing out of the cell. And these two things together, the stopping of the sodium flowing into the cell, and now the potassium flowing out of the cell. So these two things together drop the overall charge of the cell down, repolarizing it. So repolarizing it, returning. So we get back to -70 and we actually overshoot a little bit. So this is an overall negative feedback loop, basically turning off this whole action potential phase. And here we just have some characteristics of these different phases of the action potential that you can use as another way to study what's going on specifically with each of these pieces in each of these phases. Okay. And here is a comparison of our graded potentials versus our action potentials. So our graded potentials, we were thinking about signals coming in, so mostly to the cell body, also in the future to these processes called dendrites. Action potential is happening in the axon, so in our highway leaving our neuron. Graded potentials are pretty weak. We have small potentials and larger potentials. Graded potentials are variable in size. Action potentials are all or none. And so the 100 millivolts, because we're going from -70 to 0 and then plus 30 more to get to positive 30, they are always at the same exact size. The direction and change of the membrane potential for a graded potential. We can have a graded potential that hyperpolarizes the membrane, so it makes it more negative, or depolarizes the membrane, gets us towards threshold. But an action potential is always a spike up to positive 30. It's always a depolarization. Action potentials don't add together, graded potentials do. We're going to talk about refractory periods in a second, but for the future, no, there's no refractory period on a graded potential, but there is going to be a refractory period on an action potential. So that's going to be a time when you can't send off another action potential. So our channels involved in graded potentials, basically, we're thinking about the stimuli as being things that can open channels. They usually do it by binding to a channel. So we might refer to them as ligand gated or mechanically gated. We don't need to worry too much about those specifics, but for our action potential, we absolutely want to know that this is the result of triggering voltage gated channels. Okay. Okay. So next we are going to talk about those refractory periods, and maybe we will get to sending these signals down the axon itself. We know we can't change the size of the action potential, right? We can't change and make it so that it spikes up to positive 50 or something. It's always just going to positive 30. I mentioned the way that we can send a stronger quote unquote signal to like an organ in your body or something is that we can change the frequency of action potentials, right? We could send faster action potentials quicker in a row, or we could slow them down, send fewer action potentials in a row. That's true, but up to a point. There's like a maximum frequency, the maximum speed at which we can send off action potentials. There's a certain point at which the neuron is just not able to send action potentials any closer together than that. And that's because we have something called a refractory period. So a period of time where the neuron cannot become excited again. So when it can't depolarize again, right? Excitation is really depolarization, right? So we can't excite this neuron for a little bit of time after the action potential, essentially. So this is due to the action of those voltage gated channels, because we saw that time was a factor in their behavior, right? They do respond to voltage, but we also saw on that flowchart just now that 1 millisecond here, 1 millisecond there. That's because these take there is a factor of time here involved in their opening and closing. Okay. So we're going to think about absolute refractory periods, and there's absolutely no way we can send off another action potential. We're going to think about relative refractory period when it's just like really hard to send off another action potential. So the absolute refractory period is going to happen when our sodium channels, right, literally can't open because their inactivation gate is closed. Right, so our sodium channels had an activation gate here in the center that opened. Right, this activation gate opened as we were sending off our activation, as we were sending off our first wave of depolarization. And then we had that inactivation gate that swung closed. When that inactivation gate is closed, you just can't reopen it until it relaxes and gets back to its starting state. Can't do it, no way, no how. So when our sodium channels are inactive because of that inactivation gate, we are in our absolute refractory period. There's absolutely no way. And this is happening pretty much during the action potential. So as we're going up, right, we're already opening them. So there's no way to send off another action potential because we're already doing this first one. These sodium inactivation gates are closing at our peak, right? And as they are closing, they are now just closing because of that time period. So this depolarization has to happen. Those inactivation gates are closing. We can't open them up and spike back up to positive 30 when we're like here or something. Can't do that. So that's the absolute refractory period. In the relative refractory period, you know that during this during this repolarization, right, as we're going down, and then afterwards, the hyperpolarization, this is because our potassium channels are open, right? So the potassium channels are open. The membrane is especially permeable to potassium, and potassium likes to move out of the cell. So when we are in our relative refractory period, this is happening kind of right at the end of the action potential and in the little bit of time right afterwards. So relative refractory period, because that permeability to potassium is high, the potassium is leaving that cell still, bringing that cell more negative, hyperpolarizing. So even if you sent a stimulus in, you started off a graded potential that would normally get you to threshold, because we're starting so low, right? A threshold that from rest, a stimulus that from rest would hit threshold and kick off an action potential. If it happens here while we have extra potassium channels open and we're in this after hyperpolarization phase, it's not going to get us high enough, right? Because it has to overcome the fact that potassium is still leaving the cell more quickly than it usually does. So we'd have to have a really, really strong stimulus during this phase to overcome the fact that potassium is still leaving the cell. So that is our relative refractory period. So our relative refractory period is here after the action potential, where we are very unlikely to send off another action potential because we have to overcome this flow of potassium out of the cell. But we had a really, really, really big stimulus, maybe send off an action potential here. So the absolute refractory period is going to span over all of depolarization, so all of that spike to the peak of our action potential, and also most of the repolarization phase, so most of the dip back down, because we have those inactivation gates on the sodium channels closed. The relative refractory period, relatively hard to send off an action potential, is going to be the last part of the repolarization phase. But basically, we're thinking about whenever we have lots of these potassium channels open, those voltage gated potassium channels. So the second part of the repolarization phase, and then all of that hyperpolarization phase. A second action potential, therefore, is possible because our sodium channels have gone back to their resting state, right? Their inactivation gates have swung back open at a certain point. But it's really hard to kick off a new action potential because because potassium can leave that cell so easily. Right. Right. This is going to be important as we think about propagation of these action potentials. So travel of these action potentials down the axon. So when we saw that little video, what you saw was pulses of light down in that, right? So that pulse of light was tracking that positive 30 charge as it hit each piece of an axon, right? So when you see that light, that electricity as a nervous impulse, what we're saying is, where is this positive 30 charge? Where is the action potential hitting off? Where is that peak along the axon? So the action potential is going to begin at the axon hillock, and it's going to travel down this long skinny axon, and ultimately it'll get to our axon terminals at the end, where we're going to release like neurotransmitters. Okay. So what's happening, the reason I was emphasizing that time was our x-axis on our action potential, not like a spatial distance, is because we're thinking about an action potential happening at each of these pieces, right? So we'll have our little wave happening here, then we'll have our little wave happening here, then our little wave will happen here, and so on, right? So what we're tracking with that pulse of light is we're just tracking each of these peaks, right? So we're following that peak to positive 30 down the axon. Okay. So the action potential at this first section, right? So if we're looking at one section, let's say at this point we had the action potential happening here, right? So that depolarization in one patch of membrane is going to work as our stimulus for the neighboring section, right? So when this little segment of membrane gets to positive 30, that's going to affect the neighboring little bit of membrane, get it to threshold, and kick off its response, which will then also peak to positive 30. Essentially is what we're talking about. So we're going to be triggering sections of the membrane in sequence. So the action potentials are being produced patch by patch down our axon, okay? So every patch of that membrane is going to get triggered in sequence 1, 2, 3, 4, A, B, C, D, if we're breaking this up, okay? The conduction rate of an unmyelinated neuron, so we're going to talk about myelinated and unmyelinated neurons. So myelin is like a protective coating that can wrap around neurons, coming from some glial cells that we'll talk about at the end of the unit. When you think about white matter, or the fact that nerves sometimes look kind of white, some of what you're seeing is myelin, which kind of has like a lot of fat in it that gives it that color. Okay. Only some neurons have myelin. Other neurons are unmyelinated, so they're just like bare threads. So we're starting thinking about the basic ones that have no myelin. They're just these bare threads. Okay. So these bare thread neurons, these unmyelinated neurons, have comparatively slow conduction because they're going to have to trigger each and every piece of the membrane of their axon. That's not going to be the case when we think about the myelinated neurons. Okay, so what we're looking at, right, is we're triggering site A, then site B, then site C in sequence down this unmyelinated neuron. But every single site is going to have just that same little peak. That same action potential peak is happening at each site, just in order. So the action potential will be happening at time point 1 in site A. At time point 2, that action potential is at site B, and so on. All right, so we're going to zoom in on that picture a little bit more. Okay, so we're zoomed in here on our axon hillock and the first part of our unmyelinated axon. So that's what we're looking at. This axon hillock is that swelling on the left-hand side of the picture. Okay, so at rest, we know that our cell is at negative 70 millivolts, right? So negative 70 millivolts are resting membrane potential. So at rest, we're just seeing these negative charges here clustered inside the membrane, these positive charges clustered here outside the membrane. So that's our resting state. Once we initiate the action potential, so as we start the action potential, as we reach our threshold depolarization and continue to depolarize up to positive 30, that depolarization is caused by sodium ions flowing in to the cell, into the neuron. So that's what we see here in part B. So in part B, we're looking at site A, and we can see here now that the positive charges are now inside, right? So the positive charges, we're thinking our sodium ions, are now inside this little segment of the neuron, right? So that is our depolarization. That's that peak of the action potential happening here. Okay. So to trigger the next little patch of membrane to send off its action potential. What we want to note is something about like kind of space and position, right? So these positive charges, they're not like locked into that patch of membrane. They're not like glued onto the membrane. They're not bound into anything. They're just sodium ions inside the cell. So ions and molecules in general just spread out, right? We talked about reaching equilibrium in terms of concentration on opposite sides of a membrane when we were thinking about transport. So these positive charges, these sodiums, are going to move a little bit and are going to just kind of diffuse out to the sides, right? So they're diffusing to the side. And so as you move a positive charge, so a sodium ion from site A to site B, because it's just moving, it's just spreading out, right? Trying to even out concentrations. Once you move that positive charge over to site B, you've now depolarized site B a little bit, right? So if we had we were all at -70 to begin with. Site A got to +30 with its action potential, right? This starts to depolarize site B, right? So maybe we get to -60. Eventually we get to -55 as these positive charges kind of flow to the sides and just spread out. So that is how we get to the threshold for this next patch of membrane. Once enough of these sodiums have spread out, that site B gets to -55, we now kick off the action potential in site B. All right, so we can see here the action potential in site B. So now we have all these positive charges here. So I want us to look back at site A, right? So site A here, right? Before we had all our positive charges inside in site A, but now we have negative charges here, right? So what we want to realize about site A, that as we're triggering site B, in site A, we start to export those positive charges out. So we're repolarizing. Potassium is moving out. So we're moving positive charges out of site A. And we are, in fact, even hyperpolarizing site A. So we're moving so much potassium out that we go down below -70, right? So that is what's happening here at site A. And that is important to realize because as we think about site B and how it's triggering site C, you might notice something, right? Okay, so what you might be seeing, right? So site B has its positive charges inside here, right? So our positive charges, our sodiums, are in site B as we have depolarization happening at this patch of membrane. And then those sodiums just start to spread out, right? Because that's what molecules do. So they're spreading out. Some of them are spreading to the, can't do right and left, right now, but some of them are spreading to the side towards site C. But we're not controlling the direction of that spread, right? So some of them are flowing back to site A, right? They're just spreading out in every direction. But this triggers site C to send off its action potential, but site A isn't getting re-triggered, right? So even though some of those sodiums from the action potential at site B are spreading backwards, site A is not sending off a new action potential because it's in that refractory state, right? So even if these positive charges moving backwards from site B to site A get us to -55 or even -50 or something, we're not re-triggering site A because we are in this refractory state, right? So we can end up with those charges spreading out and even taking us to threshold in site A, but we won't set off another action potential by accident because inactivation gates on the sodium channels are closed during the absolute refractory period. And then during our relative refractory period, we hit that after hyperpolarization. So we're down below -70. So this is another way that we're preventing site A from getting re-triggered. So that's important because we want our action potentials to travel in a direction down the axon, right? So we want them to go from the soma, from the cell body, out to the end, out to the axon terminals. We don't want them to kind of go this way, but then also trigger that way and then come back that way. That's a problem, right? That we want this action potential to be sending a signal in a direction. And so the refractory period is really important for that purpose, because that's what stops us from accidentally triggering an action potential at the place where we just had our depolarization. Okay. So that's part of why we care about these refractory periods. So that was in an unmyelinated neuron. And now we're thinking about myelinated neurons. So what we see here is different. What we're focusing on is this myelin. So we can see this stuff wrapping around our neuron. So this is coming from some of our glial cells, which are like supportive cells in the nervous system. And they wrap around the axon and protect it. So myelin protects those neurons. It provides insulation, and it is going to increase the speed of conduction. So when we have myelin wrapping around these neurons, we don't have to trigger every single little patch of membrane anymore. We just have to trigger the spaces between, right? So we're triggering here, we're triggering here, then here, then here, okay? So we don't have to set off every little patch. We can kind of jump from gap to gap. It's literally called saltatory conduction. Saltatory, this comes from a root word for to leap or to jump, right? So saltatory conduction is jumping conduction. Right? So this is working in a similar way, except we skip little patches of membrane. We skip the patches where we have myelin wrapped around. Okay. So these gaps have a name. So the gaps between our patches of myelin are called nodes of Ranvier. So these are our nodes of Ranvier, are these gaps we're looking at. Okay. So they happen about every 1 to 2 millimeters down a myelinated neuron. We're going to see myelinated neurons are going to be some of our longer neurons, right? This is speeding up conduction here, okay? When we think about where we need our channels then, we're going to need to concentrate our voltage-gated channels in those little gaps, because those are the patches that we're triggering, right? We don't need a bunch of sodium channels here if we're not going to bother triggering that patch of membrane, right? So when we think about these nodes of Ranvier, we're thinking about the fact that we're triggering just these patches of membrane that are exposed in the nodes. So our sodium ion channels are going to be really concentrated here. So those voltage-gated sodium channels, you're going to see lots and lots of them in these little gaps, but not so much in these areas that are covered over by myelin anyway. There's kind of no point in having them there. Oh, yeah.
Which axons have myelin?
A lot of axons in our peripheral nervous system are going to have myelin, especially. Anywhere you need like a faster sort of conduction is going to have myelin. Yeah. And demyelination is a problem too in disease state. So when you start to lose myelin, places it usually is, it messes with the conduction. So things like MS and stuff are going to affect some of this myelin. Right. So here we see these myelinated axons, right? So this picture is very similar, except for we just don't have anything happening in this piece where the purple is, right? So we're jumping from a node, action potential is here. Then we jump to this node, then we jump to that node, right? Otherwise, this is the same. We're just speeding up this conduction because of the myelin. So here we have actually an example of some of our different conduction velocities. So how fast this action potential is for specific kinds of functions. So action potentials can be sped up, their conduction is sped up by adding myelin. Also, if you make a neuron wider, if you increase its diameter, make it fatter, that actually also speeds up conduction. We'll talk a lot about like how diameter affects the flow of things through a vessel when we talk about the cardiovascular system. But for now, just know increasing diameter is increasing our rate of flow, so increasing the speed here. So we can see here that based on that diameter of these neurons, we also have some types of neurons that are faster and some that are slower, right? So we can see here that our muscle position, sensory velocity, about 70 to 120 meters per second here, right? So we're going many meters per second. We can see over here our autonomic fibers are about 3 to 15 meters per second, so they're not traveling quite as far in that time period. So a thin, unmyelinated neuron is going to be pretty slow, versus a thick, myelinated neuron is going to be fast. So just realize that that M at the beginning of these is for our meters. I believe in phys lab, unless this is one of the labs they've changed, you'll be calculating at some point how fast an action potential actually travels through your body to your thigh. Okay, so we'll stop there.